Hi everyone. My name is Jing. I'm currently a postdoc at Stanford Robotics Center and the Stanford Center on Longevity. So today I'm going to talk about our recent work, the outdoor robot navigation in unstructured world. So in the following slides, I'm going to introduce our work in long-range navigation, and it covers both on-road and off-road navigation. So what is robot navigation? Robot navigation is a process where, given a goal, a robot will plan a path and autonomously move to the goal while also responding to the surrounding environment. So robot navigation can have a really significant impact on everyday life. About the outdoor applications, last mile delivery robots can make goods and services more accessible and convenient. And about the indoor applications, warehouse robots can improve both efficiency and safety by taking over the transportation and lifting tasks. So more broadly, autonomous robots can handle tedious or physically demanding work and allowing people to focus more on decision-making and higher value tasks. So the problem we are working on is the long-range navigation. It requires robots to perform autonomous navigation over a really long distance in complex terrains. So long-range navigation is really hard because it's not a single problem. It's a systematic problem, which has lots of challenges. It requires the localization, routing, perception, trajectory planning, and real-time motion control to work together reliably. So a common approach to long-range navigation is to build a really accurate global map, and plan a path within that map for robots to follow. However, constructing and maintaining a detailed map can require substantial time, computation, and also human effort. So to reduce this dependency, we assume that only a satellite map and GPS are available for global routing and localization in our scenario. But one of the challenges is that the GPS signals can be really inaccurate, especially when the robots are moving around the tall buildings or in the areas with really poor satellite visibilities. And the second assumption is that the scene understanding relies entirely on the robot's onboard sensors. So we do not assume any external sensing infrastructures or human guidance. And so compared with autonomous vehicles, for small robots, they operate under quite different constraints. So they usually have more limited sensing, computation, and battery capacities. And they also move through sidewalks and unstructured outdoor environments where they must reason carefully about terrain traversability, vegetation, pedestrians, and some social context. So one major challenge is the traversability analysis. The robot must determine whether the terrain is traversable given its own mobility and dynamic constraints. For example, as shown on the left bottom figure, the legged robots can cross curbs and stairs, while the wheeled robots can generally move around the smoother or more continuous surfaces, as shown in the left top figure. And also another challenge is that during navigation, the robot must also understand the traffic and the social rules, as shown in the figure on the right side. So to address all those challenges, we developed an approach called MOSU. It is a three-stage system for long-range outdoor navigation. So the first stage performs global routing and generates sub-goals that guide the robot in correct direction. The second stage analyzes the local perception, generates candidate trajectories, and select both a trajectory and a velocity mode for robots to navigate. And the final stage handles real-time motion and follows the selected trajectory from the last stage, while also doing collision avoidance. And for the global routing, we use a satellite map and continuously update the navigation sub-goals. And these subgoals provide the robot with only a rough direction rather than a very exact local target. So because the robot doesn't need to reach each subgoal precisely, so compared with the approaches that rely on accurate map-based waypoint tracking, the system is more tolerant to the GPS noise. So this video shows how the routing models update the subgoals during navigation. The red marker indicates the upcoming subgoal, and that guides the robot along the global road. The second stage analyzes the robot's local observation and produce a trajectory of up to around 20 meters together with velocity mode. And this stage must evaluate terrain traversability, understand social and traffic conditions, and choose a trajectory that moves the robot towards a current subgoal. And we use three main components for this task: trajectory generator, traversability segmentation model, and a vision language model to evaluate the social and traffic cues. And for traversability analysis, classical approaches usually combine the geometric local map with RGB semantic information to estimate the traversabilities, and then plan a path to a goal. These representations are very useful, but maintaining a really large geometric map can be computationally and memory intensive. Since ultimately we need to generate trajectories for navigation, and the trajectories are in very low dimension. So instead of building a really large geometric map and do a path planning for like 20 meters, we can incorporate the geometric information by directly generating feasible trajectories. So finally, we convert this problem from really high-dimensional local map building to a trajectory generation problem. And we generate diverse trajectories to cover all traversable areas in front of the robot. So in this approach, we use conditional variational autoencoder-based generator to generate diverse trajectories. And in the middle of this process, we linearly projecting the embedding vector into multiple diverse embeddings. And each of these projected embedding vector corresponds to a trajectory. So in this work, we also use a really big dataset called GND dataset to train the model for different types of robots, such as leg robots and wheeled robots. And also in the CVE formulation, the latent embeddings modeled as Gaussian distributions. So we can use the variances of these distributions to estimate the confidence of the generated trajectories. In the training, to improve the generalization across different environments and robot platforms, we created the GND dataset. The dataset contains 5 traversability categories and covers 10 university campuses around the Washington, D.C. area. And it includes around 11 hours of recorded sensor data across the environment containing more than 350 buildings. And we also open sourced the data collection and also processing pipeline to support future contributions. And this slide shows one example collected at George Mason University. The dataset includes 3D LiDAR, front-facing RGB camera, 360 camera, MU GPS, and also view odometer. So this is a video demonstration of the trajectory generation method. So in the video, the darker color means lower confidence, and the lighter color means higher confidence. And the top left figure shows the selected trajectory, which is both high confident and also closest to the target. And the top right figure shows the third-person view of the navigation. And we also use a dynamic window approach as a motion planner to follow the generated trajectory for collision avoidance. And we can see that the generated trajectories can cover most of the traversable areas. But from this video, sometimes we can also see that in some of the scenarios, those are out of the distribution cases, and the trajectories are not very traversable. So this is the next challenge we need to solve. All right. So as shown in the last video, the purely learning-based trajectory generator has limitations, and the real-world environments can contain lots of out of the distribution conditions, because our data set is not really big enough to handle to make the model fully generalized to all those environments. So to reduce this risk, we use the semantic segmentation to filter out the trajectories on non-traversable areas. So semantic segmentation is very useful for identifying terrain classes, but it's not so sufficient for higher level context understanding. For example, it may not be reliable to determine how the robot should behave at the crosswalks, or how it should respond to the pedestrians or the groups. And so we also need to handle this challenge to understand the social and the traffic cues. So we therefore introduce the vision language models to reason about the social and traffic context. So in VLTGS, we use Gemini to rank the trajectory candidates and assign one of the three velocity modes. The velocity modes include normal speed, slow, or stop. And the model considers four main criteria. The first, the selected trajectory should remain within the traversable areas. And the second, it should follow social conventions, such as yielding to pedestrians and avoiding passing through the groups. And third, it should respond appropriately to traffic cues, including the crosswalks and the traffic signs. And finally, the selected trajectory should lead the robot towards the current sub-goal. This slide shows the qualitative result of VLTGS, and the top row compares candidate trajectories from several navigation methods. And the second row shows the trajectory selected by VLTGS in red. And while the other candidates also show in gray. So across those examples, the method handles vegetation, curbs and crosswalks and corners while selecting trajectories that are both traversable and following crosswalk when the robot go crossing the street. This video briefly shows how the pipeline works in navigation. The red trajectory is the generated candidate trajectories, and the green trajectory is selected by the vision language model. So after integrating all the components together, we did experiments for outdoor navigation, and the entire travel distance is around 500 meters, and it includes various scenarios such as the sidewalks, different buildings, obstacles, and also vegetations. And we also have pedestrians on the road, and we also have the scenarios with crosswalks. So when we go to the later part, so for example, when the robot meets pedestrians, we can see that VLMs also provide the robot's velocity mode, and it ranks the trajectories and provide reasons behind the ranking. So we can see the robot can follow the sidewalks and follow the roads planned by the GPS, and the robot can also see the crosswalk and follow the crosswalk when crossing the street. And we also conducted additional experiments in various locations, including city and county areas with different terrains. And the method was also implemented on multiple robot platforms, including both the wheeled robots and legged robots. And And also in the bottom right video, at the end of this video, we can also see that the lag robot are able to go over the stairs, which means that we can also, for different types of robots, we have different traversabilities. All right, so but moving the robots from on-road terrain to off-road scenarios, there are more challenges. First, the off-road scenarios may contain dense and unstructured vegetations that robot has to find the gap to move through. And the second, the terrain may also have varying physical properties such as friction, stiffness, and roughness. And these properties also have a big effect on off-road navigation. And third, the labeled data for these physical properties in outdoor environment is very limited, which makes the purely supervised learning very difficult. So in our work, we cannot apply learning-based approaches to train the trajectory generation models because of the data insufficiency. So we come back to the classical approaches to maintain a local map. And we leverage the Gaussian splatting methods to render the environment around the robot with semantics. And to make the local map more accurately represent the geometric shapes of the environment, we also fuse the LiDAR information by Euclidean signed distance field. And then we integrate all the maps together and get the local map for planning. But semantic labels alone are not enough to determine whether the terrain is traversable. For example, when going through very dense vegetations, the robots needs to know if the vegetation is pliable to drive through. So on top of the Gaussian splats, we jointly estimate the semantic material types and physical properties. Considering we don't have a very good data set for learning outdoor terrain physical properties, we utilize VLMs to provide the guesses of multiple observations. And we fuse those values together by Bayesian inferences. As shown in the diagram, we estimate the material labels and physical property cues, and we also estimate the confidences for the regions in each image. And then we use those values to estimate the real material identity and also continuous physical properties using Bayesian inference. The continuous properties include friction, hardness, stiffness, and density, and they are estimated by Gaussian posterior, as shown in the equation, the first part on the right side. And the semantic material types include grass, wood, and soil, and etc. And they are estimated by the Dirichlet categorical posterior at the second part on the right side. This table tells how VLMs work in estimating the friction, stiffness, and the uncertainties. So we can see it's relatively good in estimating the parameters as shown in the third column. The areas with water have very least friction as the blue part. And then the grass has higher friction, the purple part. And then the soil and the pebble terrain has the highest friction, the orange part here. So it has relatively good estimation in estimating the physical properties. So from the robot observation, in this video, we can generate a local map for planning. And in the local map, the red color indicates the non-traversable areas, and the green and the gray points Gaussian splats. So from the video, we can see that using the Gaussian splats map, we can plan a path to move the robot through the unstructured terrain. So to summarize, we developed a long-range outdoor on-road navigation framework that connects global routing, direct trajectory generation, contextual trajectory selection, including understanding the social and traffic cues. And we also developed a Gaussian splatting-based local map with physical scene understanding for off-road navigation. So the goal is to enable smart robots to navigate not only around obstacles, but also through environments that require reasoning about terrain, traffic, people, and physical properties. Thank you so much. I'm happy to take any questions.